So water is 50 times less acidic in organic chemistry than physical chemistry? But water is water is water. Have you ever been taught one thing in a course, but later be presented with conflicting information in another course? Such is the case for many students in chemistry. In high school or a first-year general chemistry course in college, you're likely told or have calculated that the negative log of the equilibrium constant for the water dissociation reaction is 14. This reaction can be thought of as a weak acid dissociation, where some weak acid, let's call it HA here, dissociates into a proton plus the conjugate base A-, where in this case the conjugate base is the hydroxide ion. Since we're talking about acid-base equilibrium here, then that value 14 could also be thought of as the pKa of water. But moving on to organic chemistry, one gets this.
Water is a weak acid. Its pKa is 15.7.
All right, next we have water. Right, so what's the pKa for this proton on water? It's approximately 15.7.
And it's true that pKa tables everywhere say that the pKa of water is 15.7 or some value around that. So water is 50 times less acidic in organic chemistry than physical chemistry? But water is water is water, and we're not talking about reactions in other solvents. And we're also making the very reasonable assumption that both values are quoted at 298 Kelvin and 1 atmosphere, which is the typical condition that thermodynamic values are tabulated at. The reaction we saw earlier, H2O going to H++ OH-, can be thought of as a simplified version of what's really going on for a whole bunch of water molecules moving around in glass. From time to time, there will be two molecules doing an acid-base reaction, like this. One water grabs a proton from another, forming the hydronium ion and the hydroxide ion. That's water autoionization at equilibrium. Now, if we write out the equation for the equilibrium constant, we get K equals the activities or concentrations of H2O plus multiplied by OH and both of that over water squared. Or for the simplified reaction, K equals the activities or concentrations of H plus multiplied by OH minus and both of that over H2O. From the physical chemistry perspective, one would set the concentration of water here as 1 because there's so much water around compared to the amount that reacted to form ions, such that the concentration of water is pretty much constant. So you get the familiar Kw, or the equilibrium constant for the autoionization of water, which is given by Kw equals H2O plus multiplied by OH minus, or in the simplified version, Kw equals H plus times OH minus. At 25 degrees Celsius, the concentration of H2O plus or H plus is the same as that for OH minus, which is equal to 10 to the negative 7 moles per liter. So from that, we have Kw equals 10 to the negative 14. To get the pK value, we take the negative log and get pKw equals 14. Notice that we have pKw instead of pKa here. Since it can be tricky to define a pKa or its corresponding pKb value, you have to be aware of which species within which conjugate acid-base pair you're working with, H2O and H2O plus or H2O and OH minus. For the H2O and OH minus pair, we can define pKa equals 14, since the reaction we're interested here involves removing a proton from water. But an organic chemistry instructor will tell you that water has a molar mass of 18 grams per mole, and since water has a density of 1 kilogram per liter, 1 liter of water has 1,000 grams over 18 grams per mole, which is around 55.5 moles. So the concentration of water is 55.5 molar, and you will use that value for calculating the equilibrium constant. Before we move on further though, we've run into our first problem. The equilibrium constant for the original and simplified equations for the autoionization of water should be the same. But if we use 55.5 molar for the concentration of water, we get, for the simplified reaction with the proton, 10 to the negative 14 over 55.5. But for the equation with H2O plus, we get K equals 10 to the negative 14 over 55.5 squared. The two values are different. When you take the negative log of the first one, you get the familiar 15.7. But for the second one, you get around 17.5. But the two values should be the same. That's the first problem, but it's not the real problem. Calling the concentration of water 55.5 molar implies that you're dealing with H2O in the aqueous phase. But concentration is number of moles per volume of solvent. And you can't have a concentration for pure liquids, right? Since there's only one component. Assuming that we're dealing with H2O in the aqueous phase is where the problem is. We have a contradiction. Using H2O in the aqueous phase equals 55 molar means that all of the H2O is in the aqueous phase. But one, you can't really have all of the water in the aqueous phase as a solute, or else there will be no H2O in the liquid phase as a solvent, which in other words means you can't really have H plus and OH minus both in the aqueous phase. And two, not setting the term for water, which is a pure liquid, as 1 implies that there's a concentration for a pure liquid, which is a one-component system. But concentration, which is number of moles of solute over volume of solvent, is a quantity for a two-component system. This misunderstanding for assuming H2O equals 55 molar can be traced back mainly to a study by Ballinger and Long back in the 1960s, where they had assumed the relative strengths of acids would be the same in different solvents. But that assumption, it turns out, is incorrect. There's a really good LibreText article that talks about all this in detail, and I'll put that in the link below. Anyways, I think this example kind of illustrates the importance of evaluating your assumptions when making a claim in science. But as part of the scientific process, sometimes we only know we're wrong earlier once we've learned more later. But now that we've learned more, we really should let future organic chemistry students know that pKa equals 15.7 for water really came from a mistaken assumption. And that's more of a convention now since it's been so widely used, to avoid any more confusion on this. Though it would be nice to start to change that convention if possible. To make things clear, I'm not trying to say that you should take this video and start an argument with the organic chemistry instructor. But before things change, hopefully it makes those of you who've had or will have the experience of both general chemistry and organic chemistry more comfortable to now know that, for water, pKa equals 15.7 or 15.5 or whatever other value that isn't 14.0 is merely a convention based on a mistaken assumption. You can use it on your organic chemistry test if necessary, but do remember that the real pKa of water is 14.0.